Could you see it? Perfect. Thank you, Aidan. Okay, just few reminders before I'm starting with the last lecture that is included for the test one. Test one is in 2 weeks from today, October 16th, in B2 to 51. I think I post all this information on calendar. I already upload the PDF file of the first assignment. The due date for the assignment is Monday at the beginning of the lab. Next week labs are in the computer lab, means that does not require to have the safety glasses and the safety boots. Now, before I'm starting, the last lecture on diodes and semiconductors, diodes and diodes applications, I'll have a look in this diagram. This is what we accomplished, up to this point. We determined that we can have, the half-wave rectifier or the full-wave rectifier. Now we want to make sure that you are, or we are accomplishing, our goal is actually to have a DC output voltage. Now I'll try to make, a DC output voltage for a single half-wave rectifier or a full-wave rectifier. And this is what we want to accomplish. Now the question is, you notice that the first big step we made, or we convert the AC voltage into a DC voltage. The second step is actually to fill up, the gap. And I'll try to see if I can change the color to a different color. Now you notice that at this point, any of the two waveforms or the output voltage on the half-wave or the full-wave rectifier has a ripple. Now the question is, what is a ripple? Actually, it's the change or is the variation on the output voltage. Now, the big step we accomplished that we made a DC voltage, but the second part is to make a smooth or as a straight line of the representing a DC voltage or a DC current. Means that for a full wave or half wave rectifier, you notice that the variation on the output voltage is between the peak voltage and zero voltage. Means that somehow we have to fill up, the gap between the peak voltage. Did we change the color? Okay, let's make it a different color. Let's make it in this color. Okay, now we want to fulfill, the gap actually between two pulsating voltages. That's, for the half-wave rectifier. And for the full-wave rectifier, you notice that this gap is much smaller than the half-wave rectifier. Now, I'm going back to the previous lecture just to have a look on the two waveforms. That's, the sine wave or the AC voltage applied at the input of the rectifier. And that's, the output voltage or the voltage across the RL. What did you notice? In terms of the frequency of the output voltage. Now, let's have a look on those two. How we can define actually the frequency or the period. First of all, how we can define the period of an AC voltage. What is the period of an alternating voltage or alternating current? Yes, Andrew, that's right. Is the amount of time to complete a full cycle. Now I'm going back to this diagram, and now I'm starting, from zero. Oh, sorry. Let's choose, this. I'm starting from zero, and you notice that that's the length of time to complete a full cycle. Now I'm doing the same thing on the output. Remember that the V out or the VRL, that's your output voltage. What is the period or what is the frequency on the output voltage? I'll do the same thing. Is repetitive signal. You notice that signal or voltage. That's, the period on the output voltage or the VRL. What did you notice? You notice that the period of the output voltage is the same with the period of the V in or the input voltage. Now, that's for a half-wave rectifier. But if I'm looking for the full wave rectifier, that's probably in page 10, 11. Okay, now let's have a look on this full wave rectifier. Again, by definition, is the length of time to complete a full cycle. That's the length of time to complete a full cycle. That's for the input voltage. For the output voltage, DC voltage, now what did you notice, guys? What is the period? Repetitive length of time. What did you notice? The frequency of the output voltage is twice the frequency of the input voltage. Pay attention for these details because I'm using it a bit later in an equation. That's why I'm going back in explaining, the difference between the frequency of the output voltage for full wave rectifier and the frequency of the output voltage of the half-wave rectifier. Again, for half-wave rectifier, that's the signal and it's repetitive. Means that the amount of time or the length of time that is required for half-wave rectifier has, the same amount of time or the same period with the input voltage. Now, going back in this diagram, and you notice that the first one or the top waveform shows the output voltage for a half-wave rectifier. For a full wave rectifier, because the frequency is double the frequency of the input voltage, the gap between two pulses, you notice that the voltage is pulsating, from 0 to the VP. It's much smaller than the gap between the two pulses for half-wave rectifier. The question is how we can fulfill, this gap. In ELE150, we discussed about capacitors, what a capacitor does. Now, I'm making the assumption that it's not a diode here. Suppose that it's a step up a voltage or a square waveform. Now, suppose that again, I'm removing, the diode from the circuit. What a capacitor does. If you remember in ELE205, we made, the lab that has, the step voltage, and we have, the charging time. Now we discussed about the charging time as a value or depends on the value of the capacitor and depends on the value of the resistor. Now that's the time constant of the circuit which has a resistor and a capacitor connected to it. Now the question is, can a capacitor smooth out the output voltage? Now what a capacitor does? Now for the first half, and this is what we are looking into, having a filter. Actually, what is a filter? A filter is a block, or actually it's a capacitor that will smooth out the output voltage. What a capacitor does. Now, the same approach, suppose that for the first half, the voltage is changing or is increasing from 0 to the VP. The voltage across the capacitor is increasing, or the capacitor is charging from 0 voltage to the peak voltage minus the 0.7. We know that the diode is in the forward biased. For the second half, now once the capacitor is reaching the maximum voltage or the VP, the input voltage is decreasing. What a capacitor does, in this case, it will compensate the drop in voltage on the input voltage. Means that from the peak voltage to 0, you notice that the input voltage is dropping. The capacitor, it will try to compensate the drop in voltage. Means that the voltage V in becomes smaller. The maximum voltage across the capacitor, it's the VP minus the 0.7, and the capacitor, it will discharge the voltage, or it will discharge the current through the RL, which acts as a temporary voltage source. Remember, we talked about in ELE350 as a temporary voltage source, and we did an in-class experiment. I'm charging the capacitor, I'm keeping the voltmeter across the capacitor. Slowly is discharging. Is discharging when it's connected across the voltmeter, because a voltmeter has a resistance, an internal resistance in it. Means that in the same way we can look for the load resistance. You notice that the low resistance, it's connected across the capacitor, and the capacitor, it slowly discharge, and the current, it's supplied to the through the load resistance, decreasing slowly the voltage. You notice that from the peak voltage, the input voltage is decreasing to 0. Now the negative voltage is suppressed due to the halfway rectifier, due to the diode. Means that for this period there is no voltage supplied to the capacitor. For the second waveform, or for the second sine wave, you notice that the voltage is slowly increasing when the two voltages are the same, and the capacitor voltage, or the voltage across the capacitor, it will increase again to the maximum. As a result, instead of having a ripple between the 0 and the VP, now we have, I may change the color to a green one, let's say. Now I make it probably in this way. Okay, now the capacitor is charging, and after that, when there is no voltage, it will act as a temporary battery, and after that is charging again due to an increase in voltage. Now that's a repetitive process, and you notice that the output voltage is or looks like, or reassemble a DC voltage. We still have a ripple, but it's much smaller than it was before. The initial ripple was between 0 and the VP. Now the ripple is much smaller. Just to remind you again, what means ripple is the change in voltage, or the variation in voltage between the two limits. You notice that on the lower side, or the lowest value is 0, or at this diagram, you notice that the lower side, or the minimum value, or 0, and the maximum voltage is VP. That's the maximum ripple. That's the voltage, the output voltage of the unfiltered halfway rectifier. That's the output voltage of the unfiltered full wave rectifier. And compare with, the two diagrams, you notice that at this point, instead of having, a full ripple or a maximum ripple, the difference between the maximum voltage and the minimum voltage, now we have, the output voltage between the two limits. Means that we are reducing the ripple or the variation or the pulsation of the output voltage by simply adding a capacitor. Again, what we are doing here, it's, the RC type circuit. The variation or the ripple of the voltage depends on the capacitor and depends on the resistance RC. To remember that, the time constant or the tau of the circuit depends on the capacitance and depends on the resistance connected to the circuit. Now, the main difference, between the full wave and half wave rectifier, you notice that for the half wave rectifier, the capacitor has to compensate a pretty long period of time. Actually, it's, the area underneath, when the voltage is zero. For the full wave rectifier, the capacitor does not have to compensate a very large amount of time as the half wave rectifier. Between the two, you notice that the capacitor is, or for the same circuit, let's suppose that we are making, an assumption that we have the same capacitor and the same RL resistance. Now, for the same RC type circuit connected to a half wave rectifier or connected across the full wave rectifier, again, the assumption is the same resistor, the same load, the same capacitor. For the same voltage, you notice that the full wave rectifier or the full wave or the filter for the full wave rectifier is more effective. Means that for the same capacitor, the same resistor, the ripple on the full wave rectifier is much smaller than the ripple on the half wave rectifier. Means that for the purpose of reducing or smoothing the output voltage, the full wave rectifier is, much better in terms of the efficiency compared with the half wave rectifier. Not always we need a full wave rectifier. Sometimes, in some basic circuits, we may need a full wave rectifier. Just to give you an idea about the ripple that we may want to achieve in practical applications. Usually, most of the AC to DC converters, consumer class, let's say, usually it's around, 100 millivolts ripple. A good UPS, a good AC to DC converter. Usually it's, in about or in this range, 100 to 100 millivolts a ripple, which quite, reassemble, the our goal, to have a nice smooth output voltage as a DC or as an ideal DC voltage or DC current. Some other, let's say, better AC to DC converters may have, 15 millivolts, and in a good class for, a good converter or a good power stabilizer, will see bitrate or a regulator, it will have 10 millivolts or less than 10 millivolts. Just to give you an idea about, usual or practical or general purpose or general use ripple voltage, a bit, in a medium class, and very high class or a good class converters or filters may have 10 millivolts or less than 10 millivolts. 10 millivolts compared with 5, 10, 20 volts voltage represent a very small variation or a very small ripple um, on those voltages. Now we have to do the calculations when we are doing some uh, rectifiers. Now, where we are using rectifiers, you may use a rectifier. We may have to design a rectifier in your capstone project. That's why I'm showing just the basic of those rectifiers and the practical equations and formulas that may be used to do just the minimum calculations that is required to design a rectifier. Now, the peak-to-peak voltage, that's the rectified voltage, which has a very small ripple. You notice that always the ripple or any quantities or any characteristics for a ripple is symbolized by the small letter r. V is the voltage, R is of the ripple, peak to peak is the P and P notation. Sometimes you will see PK dash PK, but has the same meaning. Now the middle point is what we measure with a meter, and that's the VDC or the DC component of an output voltage that has a ripple in it. Now that's the peak rectified. That's the maximum voltage or the peak voltage rectified when there is no capacitor connected into a circuit. That's much easier to understand, the two quantities, the VDC with capacitor, the VP rectified without the capacitor, and the VRPP. Usually in the electronics, the most important factor is the ripple factor. The ripple factor, or simply the lowercase r, is the VRPP, means that the peak to peak of the ripple of the output voltage over the VDC. Now, there are two calculations, two equations, and two formulas that are given for the first test. First of all, how we can determine the VRPP, or the peak ripple voltage, is 1 over the frequency multiplied by RLC. Remember that, the time constant, the RC that we used, before, and multiply by VP rectified voltage. Now, VP rectified voltage, we know how to find that. It's, the input voltage of the full wave rectifier minus the voltage across the two diodes, the D1 and D2 in our previous presentation. Now the question is how we can determine, because we are looking for the VRPP, and that's a very good approximation. There are some other equations which are more let's say complicated than the one that is already provided in this course. Another approximation, or how we can determine actually what is the DC, or what we measure as the average, between the mean and the max, is 1 minus 1 over 2 times the frequency multiplied by RLC. Now, pay attention for those details. It's the frequency for a full wave rectifier, or the twice the frequency of the input voltage. The frequency of the output frequency. That's why I made a clarification in terms of the frequency. And I start, going back in the previous lecture to emphasize that, the frequency is always twice the input frequency, or the F in multiplied by 2. For example, if the frequency, the input voltage frequency, or the V in frequency is 50 Hertz, what we are using in this calculation is 2 times F, which is the input frequency, multiplied by 2, which is 100 Hertz. Remember, we talk about, those two diagrams. That's the same frequency for the halfway rectifier. And for a full wave rectifier, you notice that the frequency is doubled on the output of the bridge rectifier. It doesn't matter if it's a center tap using 2 diodes or a bridge rectifier. Always the frequency of the output voltage is twice the frequency of the input voltage. That's why I review, this part of this component. And I put that in writing. The frequency, it's actually twice, the frequency of the input voltage. Now, just a small, excuse me, a small observation in this circuit. You notice that when we are connecting the transformer with the bridge rectifier, if you remember, we talk about, the charge current. The highest current is when the capacitor will start charging, means that it will draw a very large amount of current. Actually, this current can be quite high depending on the value of the capacitance, which may actually destroy, may burn, one of the diodes. That's why you may see a small resistor, and that's, the surge resistance. Usually the purpose of this resistance is to limit the charging current when the capacitor or the circuit is the first time connected on the voltage source, or the switch is closed. You notice that the instant of time when the switch is closed. After that, the capacitor, when it's charged, it will have, a small amount of current that is required for charging and or discharging. This resistance that you may see it, in different circuit may be anywhere between few ohms, like 1, 2, 3 ohms to 10 ohms, probably sometimes, 15. But I would say most of the time is between 1 and 5 or 1 and 10 ohms. That's why you may see a small resistance value that it's connected in series with the capacitor. Again, the purpose of this surge resistance is to limit the current that flows through the diodes when the switch or the rectifier is the first time connected to a voltage source. Now we'll move into a supply or power supply regulators, and this is, most of the time what we are using at home. Suppose that you have, an AC to DC converter that it's used, to charge your phone, to charge any, devices at home, or just, for the general purpose applications. Now, in the block diagram for a DC power supply, you notice that there are 5 different blocks. Now, from the beginning, we have, a transformer. Most of the time, we are using, a step-down transformer. For example, 120 volts to 10 volts, to 20 volts, to 15, to 7, 8 volts, and so on. The diode rectifier, I said that, most of the time we are, because this transformer is not a center type transformer, we may have to use a bridge rectifier to have the maximum efficiency of the rectifier. after, the voltage is converted, the AC voltage on the secondary of the transformer, now it's converted into an output voltage, which is the rectified voltage. The rectified voltage now is filtered using a capacitor, and you may see a voltage regulator. Now, next week, we'll start with a Zener diode, but at this point, I'm presenting a voltage regulator, which will maintain, which will keep, the output voltage, which looks like, a very constant value. That voltage regulator, it will maintain between two limits, the minimum and the maximum current, if a load is applied to it. Means that most of the time, if you are measuring the voltage on an AC to DC converter, it's about 9 volts, 7 volts, 5 volts, and so on. And the load is limited. You notice that any of the chargers or any of the AC to DC adapter, always it will have a maximum current. If the current is higher than the maximum current, usually they have an internal protection that it will short circuit actually it will cut off the voltage on the output. Some of them does not have that, and we may burn actually the voltage regulator. But up to this point, we may see those 5 blocks of a power supply or a power supply regulators. Now, I'm focusing on those voltage regulators. We cover everything up to this point. Means that we make a very nice smooth output voltage with a very small ripple. Now we are looking to have a constant voltage using a voltage regulator. What a voltage regulator does, it will make almost or nearly constant output voltage. For example, I'm looking for 5 volts. This is most of the time that it's used as the USB charger, the 5 volts, or any other chargers may have 7 volts, 8 volts, 9 volts, 12 volts, and so on. The idea is to have a constant output voltage with a very small amount of ripple. Usually it's the ripple rejection, or it will smooth out the output, that it will make almost like an ideal, and that's why I'm trying to clean up that diagram, as an ideal voltage source. Now, what a voltage regulator does, first of all, let's try to clarify what is in it. Has more electronic components in it. Is not just a diode, is not just a resistor, it's actually an integrated circuit. We may see this abbreviation as an IC, integrated circuit, which has multiple components or devices in it. Means that it's a combination, or has multiple blocks. And we'll discuss about integrated circuits in op amps when we are going into details. An integrated circuit may have a lots of semiconductors, transistors, diodes, has resistors, has capacitor. Means that it's a small size of a circuit that is already embedded in a device. Now, usually we are having a positive output voltage. You notice that, sorry, that's the output positive voltage, and this is what we are looking for, to maintain or to obtain a constant 5 volts. Usually for a positive output voltage, you notice that it's positive 5 volts. The 7, 8, it's the first, or are the first 2 digits. 8 is showing you that is a positive voltage. 7/8 is standardized for the voltage regulators. Everything else, stays the same. We still have, those 5 blocks. We have, the transformer, we have the rectifier, we have, the filter. The next block is the voltage regulator, that it will maintain a 5 volts output voltage, and the last block, it will be the load. Means that the voltage that is provided to this voltage regulator has to be a bit higher than the 5 volts. We are not applying 5 volts and expect 5 volts on the output. We know that all the semiconductors, it will have some voltage drop across them. Means that in order to obtain the output voltage as 5 volts, I have to apply probably 6-7 volts on the input of the regulator. Now, in the same time, we may see that some circuits requires a negative voltage. Now, the difference between a positive voltage regulator, as in this example, and a negative voltage regulator, as in this diagram, you notice that the other regulator, it has the first 2 digits at 7, 9. That second digit 9 is showing that the output, it will be a negative voltage. The 7, 8 or the 8 as the second digit means that the output voltage is a positive voltage. Now we may see fixed voltages, or the other 2 letters in front of the numbers is most of the time based on the manufacturer. We may see different letters like LM, NE, MC, depending on the manufacturer. Is not critical to determine the first 2 letters. It's just the manufacturer. Sometimes it's just a single letter, sometimes just 2 letters, sometimes 3 letters. But the 7/8 or the 7/9 XX, it will determine if the regulator is a positive or is a negative voltage regulator. Those regulators become standardized in voltages. I said that 7/8 means that it's a positive voltage regulator. The last digit shows you or gives information about the output voltage. 7805 means that the output voltage is 5 volts. 7806, the output voltage is 6 volts, and so on. We may go up to 24 volts. In terms of the case, we may see that package or that case which has a metal sink. Sometimes you will see this heat sink or a metal sink that is connected to another large heat sink. I will show you in lab next week a bridge rectifier as a single component, and I will show you those transistors or the voltage regulators that looks the same. What we have to determine is the code or the type number that it's printed on that. Now I mentioned that 78XX can be 0, 5, 0, 9, 24 and so on, has a positive voltage. The other one which has identical voltages, for example, it's 795, that's 5 volts, or 795.2. you notice that we may see a small variation of the 5 volts, which is .2, or 5.2 volts, 6 volts, 12, 15, 18, 24. they are coming, in almost, the same ranges as 7800, except that, and that's why I put it in notes, except that 79 XX series has, a negative voltage. The other difference is in terms of the pins. Pins 1, 2, and 3. You notice that for 7900, the pin 1 is on the ground. The pin 2 is the input. Pin 3 is the output. For the 7800, pin 1 is the input. The second pin, which is, the middle pin, is on the ground, and the third pin is the output. They make, this convention for 78 and 7900 in order to avoid, burning actually the another circuit, or burning, the another device that is connected to a voltage regulator that probably it was replaced with 7900 instead of 1800, and vice versa. Now, in terms of the performances, there are actually two ways to determine the regulation performance of a power supply. The first one is in terms of the line regulation. This line regulation refers to the same load, the same voltage regulator, and suppose that the input voltage has a small change. How that small or that change in the input voltage, it will affect the DC output voltage. This line regulation can be defined as the change in the output as a function of a change in the input. Means that I'm not changing the load for a constant load. I'm changing the input voltage to determine the change in the output voltage as the input voltage is changed. That's not very useful, or is not used in many applications. The example that is made, suppose that the output is or has a change in 1.5 millivolts as the input voltage is changed by 1 volt. What will be the line regulation is 0.15%. That's a very good indication on how the power supply, it will act as the input voltage has a small change in the input voltage. The other one is, probably more important, and I'm using, something, similar with this load regulation, which is called the voltage regulation in electrical machine. In electrical machines that we'll discuss, next term, the ELE350, we'll talk about the voltage regulation, or the PR, the percent voltage regulation. The change in the output voltage from the no load to the full load voltage. What means, again, the full load and no load? No load means that there is no resistance, or there is nothing, connected on the output, and the full load value, it's the nominal value, or the maximum resistance that can be connected on the output of the voltage of the power supply to maintain a maximum current. Means that this voltage regulation is more used in electronic, in generators. We'll talk about the percent VR, or the percent voltage regulation. Means that between the two, I may use probably the load regulation, which is actually the voltage regulation more intensely, and has it's probably one of the most used parameters in order to estimate, the behavior of the output voltage as the load is is changed. Now, in terms of troubleshooting, I'm just giving some ideas. We have to check uh, the parts, the components. Now we know what we expect, and we have to visualize the waveforms. Not always having a voltmeter or a multimeter is enough to determine or to troubleshoot a power source. First, start the supply voltage. Do we have the input voltage? Sometimes is just the fuses, and sometimes it's just the input voltage or the transformer that may be wrong. Sometimes you'll have the sensor that must be checked. We can have a visual. We can smell if it smells anything like burn, or any other components that has to be replaced using an oscilloscope. Now, again, not always is possible to troubleshoot a power source or any electronic components or modules um, in an equipment without having an oscilloscope. Sometimes it's enough to have just a digital multimeter. Now, having an oscilloscope, and I'm showing how to use the oscilloscope. In the block diagram, we talk about the transformer, the full wave rectifier, capacitor, voltage regulator, and the fifth block, which is the load. We may see in the block diagram that may be supplied by the manufacturer. We may see those TP or PT, test point or point of testing. I'm using both of them. That's why I just want to make you aware that you may see the TP or simply the P1, P2 as point 1, point 2. TP most of the time stands for the test point or the point of test or the PT. Now, having an oscilloscope will make much easier to identify or placing the oscilloscope in different testing points, and we know what to expect at the beginning of transformer or the input voltage for a transformer. We know to expect the output voltage of a transformer. Full wave rectifier, you notice that the AC voltage converted into a DC voltage, the capacitor input filter, and the voltage, the input for the voltage regulator. What to expect on the output? A straight line, which means that the regulator or the voltage, it will maintain a constant voltage. Now that's an example of what to expect if we are not seeing any voltages after the diode, which acts as a half-wave rectifier. If there are no voltage on the output of the diode. Now, most of the time we are dealing with an open or a diode which has a voltage of 0. Now, we mentioned that we may have two different cases. We may have a short circuit or an open circuit for a faulty diode. Now, we may end up having a sine wave form at this point, or in this example, we may have a straight line, which indicates that there is no voltage at the end or the cathode of the diode. Practical applications, AC to DC converters, simple diode circuit. We may discuss protective circuit a bit later, but next topic, which is about the Zener circuits or Zener diodes, and that's the next topics that it will be posted on D12. Again, I'm trying to post the set of lectures for the test 2 over the weekend. Means that this lecture is included for the test one. Starting from next week, all the other lectures or another, 5-6 lectures, it will be posted on D12 for the second test. Any questions, comments, concerns, please? Any questions, comments, concerns? If you don't have any questions, have a nice weekend, guys. Thank you. And don't forget, the due date for the assignment is on Monday. Thank you, guys. Thank you, Graham. Yes, Aiden. Yeah, usually you should have, a capacitor, a small size is called decoupling capacitor. You notice that those diagrams has, just few micros. The largest capacitor, it's right after the bridge rectifier. Usually that capacitor is few hundreds or few thousands of microfarads. The other two small capacitors that are connected at the input and the output of the voltage regulator is called decoupling capacitors and has, a very small value. Actually, it will maintain a smooth output voltage. It will act as a buffer for the rectifier, actually for the regulator. Did I clarify that? Did I answer your question, please? Thank you, Hayden. Any other questions, please? Sorry. The average current. Keep in mind that if we are looking for current as the average, we have to find actually what is the average voltage. Once you know the average voltage, knowing the resistance value, we can find the average current. And in top of that, knowing the average current or average voltage, we can determine what is the average power. Means that everything is related, to the average current, average voltage, or average power. Yes, I know it's not specified. It's given in RMS, but you have the equations that are already given for half-wave or full-wave rectifier to determine the average, which is actually the DC. Remember that, the average or the DC voltage or the DC current. Most of the time, those equations are in terms of the voltages. But once we know the voltage, we know the RL, we can determine what is the average current, what is the average or the peak voltage, the peak current or the peak power. Again, it's just, the Ohm's law or the Watt's law, nothing else. Did I answer your question, Aiden? But look in your notes, you have, the average voltage or DC voltage has the same meaning. Look in your